Look inside any modern device, past the complex processors and digital interfaces, and you will inevitably find the entire system relying on a single, universal building block. This is the operational amplifier, or op-amp. It is an analog computer etched onto a single chip, capable of executing mathematical commands based on physical voltages. Out of the box, its behavior is essentially a blank slate. The exact function of an op-amp is defined entirely by the external components and engineer wires around it. By arranging those components, we can program this chip to operate across 5 distinct domains: mathematical operations, nonlinear conditioning, waveform generation, frequency filtering, and power regulation. Understanding linear integrated circuits, then, means learning how to program this specific differential architecture to execute whatever task the system requires. To understand how it works, we start with a theoretical model. The ideal op-amp has infinite input impedance, blocking all current from entering its terminals, zero output impedance to drive any load seamlessly, and an infinite open-loop voltage gain. That infinite gain creates an immediate problem. Without intervention, multiplying any tiny input signal by infinity causes the amplifier to instantly overload. The output maxes out against its physical voltage limits, a condition known as clipping to the rails, making it entirely useless for linear scaling. We control this raw power using resistive negative feedback. By looping a portion of the output voltage back into the negative input terminal, we force the op-amp to continuously self-correct, taming that infinite gain into a precise, manageable multiplier. With that stability locked in, the op-amp can perform exact linear math. It can invert signal polarity, act as a voltage follower to buffer delicate circuits without drawing current, or sum multiple voltages together into a single output. But silicon is a physical material, and eventually the ideal mathematical model completely breaks down against the uncompromising laws of physics. This diagram illustrates slew rate. Notice how a perfectly vertical square wave enters the op-amp, but the output emerges sloped. Slew rate is the absolute physical speed limit of the amplifier. The output voltage cannot change instantaneously. It takes time to swing from one extreme to another. Another physical limit is the common mode rejection ratio, or CMRR. In the real world, ambient electromagnetic noise infiltrates both input terminals equally. A high CMRR allows the op-amp to subtract and ignore that shared interference, isolating only the intentional difference between the two inputs. Negative feedback is the engineering mechanism that forces this raw, volatile silicon into a reliable mathematical instrument. Linear precision is only half the equation. We can deliberately abandon those constraints by removing negative feedback entirely to see what other capabilities emerge. Instead of stabilizing the circuit, positive feedback routes the output back to the positive terminal. Any minor voltage fluctuation is amplified, fed back, and amplified again, until the output violently snaps and locks to its maximum voltage limit. We use this snapping behavior to build comparators and zero-crossing detectors. These circuits stop scaling voltages and start making absolute binary decisions. If input A is higher than input B, snap high. If not, snap low. A highly specialized application of this logic is the Schmitt trigger, which relies on a mechanism called hysteresis. Look at this input signal. Hysteresis establishes 2 separate threshold levels for switching. As the jagged, noisy analog wave crosses the upper threshold, the output snaps high. It will not drop low again until the signal falls past a completely separate lower threshold. This gap prevents the noise from causing the output to flicker rapidly back and forth, extracting a clean digital square wave. Sometimes the noise isn't an artifact to filter out, it is actively burying the data we need. For that, we return to linear operation with the instrumentation amplifier. By networking 3 separate op-amps together, an instrumentation amplifier mathematically maximizes the common mode rejection ratio. This extreme precision extracts faint microvolt signals, like human heartbeats, out of massive electrical noise floors. By mastering these nonlinear and specialized topologies, we force the op-amp to bridge the ambiguous variations of the analog world with the strict binary logic of digital systems. The system changes entirely when we introduce reactive components into the feedback loop. Adding a capacitor shifts the op-amp out of static math and into the dynamic frequency domain. Combining resistors and capacitors creates an RC network. Because capacitors take a specific amount of time to charge and discharge, this network introduces physical time constants to the circuit. Pair that RC network with positive feedback, and the op-amp becomes an oscillator. Relying solely on the steady charge and discharge cycle of the capacitor, the circuit generates its own continuous sine, square, or triangular waves, requiring no external input signal at all. For purely timing-based operations, engineers often rely on a dedicated alternative, the 555 timer IC, which is specifically optimized to generate stable astable pulses or monostable delays. If we take that same RC network and pair it with negative feedback, we achieve the opposite effect. We create active filters. Passive filters, built only from resistors and capacitors, inherently weaken the signal as they process it. Active filters use the op-amp to provide precise voltage gain, ensuring the signal is driven forward without attenuation, even as specific frequencies are blocked. The standard for this active frequency conditioning is the Butterworth filter topology. This Bode plot shows the frequency response of a Butterworth design. It is engineered to achieve a maximally flat passband, meaning all desired low frequencies pass through with absolute uniformity before it sharply drops off to slice away unwanted high-frequency noise. By rearranging the RC components, we can reconfigure the filter to pass high frequencies, isolate a narrow band of target frequencies in the middle, or create a notch filter to surgically remove a single interfering frequency tone. Capacitors transform the op-amp from a static calculator, acting on fixed voltages, into a dynamic engine capable of manipulating signals over time. Up to this point, we have treated the op-amp strictly as a low-power information processor. Now we apply its logic to managing heavy electrical current. In a voltage regulator, the op-amp acts as the intelligence of the power supply. It continuously compares the actual output voltage against a fixed, stable reference voltage. Look at this flow of power. Whether configured as a series or shunt regulator, the op-amp detects any drop or spike caused by the load and instantly commands the power transistors to compensate. A messy, fluctuating input enters on the left, and a perfectly flat, stable DC voltage is delivered on the right. This regulatory framework is so critical that entire chips are designed specifically to encapsulate this comparative logic for power management. To achieve maximum efficiency, modern systems use switching regulators. By pulsing power on and off incredibly fast, buck regulators step voltage down, boost regulators step it up, and buck-boost regulators do both without wasting energy as heat. Managing that much current carries inherent thermal danger. These circuits must incorporate current sensing and foldback protection to automatically choke off the power supply if a short circuit threatens to melt the hardware. The exact same differential logic used to analyze tiny microvolt signals guarantees safe, unyielding power delivery for heavy industrial systems. We have built a complete system. We scaled up from linear math, applied nonlinear conditioning to digitize data, harnessed frequency dynamics to sculpt waveforms, and secured the hardware with regulated power. Every one of these functions stems from a single differential amplifier architecture that scales to solve almost any hardware problem imaginable. The ability to manipulate feedback loops, match impedances, and control frequency response is the true essence of analog system engineering. This collection of circuits functions as a programmable toolkit, allowing engineers to dictate how voltages and currents interact across varied physical applications.